In this video, we're going to work through an example using the central limit theorem for proportions. So suppose that we have a large university, and at this university, about 60% of students are registered voter. We're going to take a random sample of 500 students. So the first thing I'm going to do is just lay down some information that will be helpful. Our sample size right here is 500 students, so we know that n is equal to 500. And then we also want to think about the population proportion, which usually is not something that we have, but we're going to pretend that we have this number for a moment. And about 60% of these students are registered voters, so P is about 0.6, or 0.60 if you'd rather. And let's hop into our problem right here. Number one says, what is the population under consideration? In this case, what's the large group that I'm trying to understand? And in this case, I'm going to talk about students at this large university. You might think about students at this large university that are registered voters, but hold on to that. We're going to use that in just a moment. I want to think about what's the group that I'm trying to make a statement about. In this case, it's just students at this university. So students at the university. At the university. Excellent. Number two says, what is the population parameter? So remember, the population parameter is a piece of information I want to talk about from the population. It describes the population in some way. So I'm looking at this number right here, or this number over here, P equals 0.6. This is going to be a descriptor about the students at my university. So in this case, we're given a percentage or a proportion. So the parameter that I'm going to use is P, which is the population proportion. And I also want to talk about what this is actually going to be describing. I do know that the value of P is 0.6, and we'll give that with our answer in just a moment. But I want to describe what that number is talking about. In this case, this is going to be the proportion of students that are registered voters. That are registered voters. And I guess I should be a little bit more specific here. Proportion of students at this university, because the population proportion has to come from, well, the population that we just talked about, students at the university. So we do want to be specific here. So the value of this is actually given to us. We said that was 0.6. Now, usually knowing that the value of the population parameter is pretty difficult to do. We can usually only estimate it, but perhaps we've got some data that we might not otherwise have access to. So we have our population, we have our population parameter. Number three says, verify the conditions of the central limit theorem. There are two and a half conditions for the central limit theorem that we want to talk about. So the first one is independence. And independence tends to be a difficult thing for us to verify because it has to get into the nitty-gritty of how we took the sample. For our purposes, what I'm going to look for is just, do we have a random sample? And in this case, if I look up here, yes, I do have my random sample of 500 students. So I'm going to say, yes, we can assume that our sample is independent. So we want to make sure that we have independent sampling. The other thing that we need to verify is called the success-failure condition. And this tries to make sure that our sample size is large enough. The success-failure condition is essentially just how many successes and how many failures would we expect to see in our sample. And the way that we calculate this, we want n times p, and we want n times 1 minus p. Now, these both need to be greater than or equal to 10. And that just verifies that my sample size is large enough. I don't usually care about the actual value of these numbers as long as they are both just greater than or equal to 10. That's all that really matters. So here I do have just a bit of calculation to do. So n times p, well, that's going to be 500 times 0.6. So in this case, I'm going to grab my calculator. 500 times 0.6 is 300. Well, that is certainly greater than or equal to 10. So yes, we do meet that condition. And then I want 500 times 1 minus 0.6. Let me make sure I'm not going to make a silly mistake here, but this should be 200. Yes, it is. That is also greater than or equal to 10. So that is something that we can usually show in this case. Independence it's very, very difficult for us to show, but we can show the success-failure condition. And if I ask you to verify a condition, usually it's going to be the success-failure condition. So that's something that you're going to want to be comfortable with. So that means, yes, that the central limit theorem applies, and the central limit theorem says, hey, that means that the sampling distribution of p hat is normally distributed. And if I want to talk about the normal distribution, I probably need a mean and the standard deviation, and that's what number 4 is going to ask me here. It says find the mean and the standard deviation of the sampling distribution. So the mean of this sampling distribution, I like to use mu sub p hat. So this is going to talk about the mean of the various p hats that we could have. That is always equal to the population proportion, p, which in this case we do have. That was given to us. We said that was 0.6 earlier in the problem. So the mean is just the same as the population proportion if we have it. The other thing we got to talk about then is the standard deviation. So the standard deviation of the various p hats. This one is a little bit trickier for us to verify. We need to do a little bit of work here. The standard deviation, and I should say very quickly, some problems might use the term standard deviation. Some might use the term standard error. So some, and actually I really technically should be using this standard error. But for what we're going to use it for, we can kind of treat that as the standard deviation. That's going to be something that we can kind of use, at least for our purposes, interchangeably. Standard error and standard deviation are basically going to mean the same thing for our class. But if I want to calculate the standard deviation or the standard error, we might use SE for standard error. I want to use the formula square root of p times 1 minus p divided by n right here. So here I'm going to have to do a little bit of calculation. Whoops. We said p is 0.6 times 1 minus 0.6 divided by n is, we said what, 500 was our sample size. So here we are going to have to grab our calculator. Square root of 0.6 times 1 minus 0.6 would be 0.4 divided by 500 gives me 0.0219. I'm going to round to 4 decimal places here. Because we're working with generally small decimals, we want to be very precise. So I'm going to use 4 decimal places for my standard error. So here's my mean is 0.6, and here's my standard deviation. And I'm actually going to copy that down here. My mean of the p hats is 0.6. The standard error, or the standard deviation, if you rather, of the p hats is equal to, we said 0.0219. We're going to need that in the next couple of problems. So moving on to number 5, here we're going to start to get into some probability questions about this distribution. So this says, find the probability that in our random sample of 500 students, 310 or more are registered voters. So the first thing I'm going to do really quickly is draw out what this is going to look like. We said that we did meet the conditions of the central limit theorem in number 3, which means that when we look at the distribution with this mean and this standard error, we get something which is normally distributed. So that means that we get to assume that we're working with normal distribution, which is really, really nice because we know a whole heck of a lot about normal distribution from our last chapter. We know that the mean is 0.6, so we have 0.6 right here in the middle. And usually when we talk about this, we're going to talk about a data value. Now, one thing I'm going to highlight here is that here this is a proportion. Here they're giving us a raw number of 310 or more. So I need to find a way to make that 310 into a proportion. Well, luckily for me, I know that that 310 is out of my 500 students. So in this case, I need to take just a moment to find, the sample proportion, which is p hat. So p hat is equal to, 310 divided by 500. So let me grab my calculator real quick. 310 out of 500, I ended up with 0.62. So 0.62 is my observation. I know that that is greater than 0.6, so that's going to live somewhere over here on the right. And I want to be able to talk about 310, going back to this, or more. So that means we want the area to the right. We're going to be talking about this area over here. So at this point, I can use what I know about z-scores, and I can say, all right, well, I know this is my mean, this is my standard deviation, this is my data value. Let's get right to it. We should have everything we need. So the z-score corresponding to 0.62. Remember, our z-score formula would be x minus the mean divided by the standard deviation. The only changes I might make to this formula is to say, we're talking about the mean of the sampling distributions of the p-hats and the standard deviation of the sampling distribution of the p-hats. So x is 0.62 minus my mean, we said that was 0.6, divided by our standard deviation, which we said was 0.0219. So we're going to try to find the z-score corresponding to this. 0.62 minus 0.6 divided by 0.0219. I ended up with a z-score of positive 0.91. For z-scores, remember, we really only need 2 decimal places because that's all our z-table is going to tell us. So we have a z-score of positive 0.91. The only thing I have left to do is to find the area to the right of that. In that case, I'm going to need my z-table. So let's hop over to my z-table real quick. We said 0.91, positive 0.91. So here's the positive case. Let me erase so that we can start fresh. We said z is equal to positive 0.91. So let's see, here is positive 0.9. We're looking at this row right here, and 1 would be this column up here. So I must be talking about an area of 0.8186. However, we have to remember that that 0.8186 is the area to the left, is 0.8186. So if I want the area to the right, which is what I drew in my quick little sketch, is I need to subtract this from 1 because I know that this is the complement of what I want. So I want 1 minus 0.8186. Let me hop back to this example. So to find this area, I want 1 minus 0.8186. This will tell me my probability. So 1 minus 0.8186 gives me 0.1814. There is my answer. So it takes a little bit of setup with these, and as with all of our normal distribution problems, I think a drawing is really going to help you out if you make a quick rough sketch, along with listing what is your mean and what is your standard deviation. Let's take a look at one more example here. So jumping down, and actually before I get too far ahead of myself, I'm going to write down the mean and the standard deviation once more just so that we have it in front of us. We said the mean was 0.6 and the standard deviation, or perhaps the standard error if we want to use that terminology, is 0.0219. Okay. So number 6, last example for this video, it says find the probability that in our random sample of 500 students, fewer than 275 are registered voters. So again, I'm going to draw out what this looks like on my curve. We met the conditions for the central limit theorem, which says that the sampling distribution of p hat is normal. Our mean sits right in the middle here is 0.6, and we need to start by finding what is our particular p hat, in which case I have fewer than 275 out of 500. So 275 divided by 500. Let's go ahead and divide that out. I have 0.55 for that p hat. So that number is less than 0.6. It's going to be somewhere over here on the left. Here's 0.55. And then if I want to talk about this area, this said fewer than 275. Fewer than meaning the area to the left. I must be talking about this area over here. So just like last time, I need to start by finding the z-score corresponding to this p hat, and then once I have that, I can use my z-table. So my z-score, we said, was x minus the mean of the sampling distribution divided by the standard error or the standard deviation of the sampling distribution. So x is 0.55 minus my mean, that was 0.6, divided by my standard deviation, 0.0219. And let's go ahead and divide this out. 0.55 minus 0.6 over 0.0219. This time I ended up with a z-score of roughly negative 2.28 for my z-score. So I have negative 2.28 as the z-score corresponding to 0.55. The last thing I need to do then is just find the area to the left of this using my z-table. So hopping back to my normal distribution, we said negative 2.28, so we're going to take a look at my negative z-scores right here. Negative 2.2, we must be talking about this row right here, and 8, we're talking about this column. So that means that the area to the left in this case would be 0.0113. Luckily for me, that's exactly what I wanted. I wanted area to the left, so I don't need to do anything with this number. I don't need to subtract it from 1 because this is already telling me the area to the left. So 0.0113. Hopping back just so that I can write my answer, this probability is 0.0113. There is my probability. So I would strongly encourage you, as you're working through these types of problems, to take a moment and specifically to write out what is the mean of your sampling distribution, what is the standard deviation, and what does the picture look like. And that's going to help you when it comes time to finding your z-score and then finding your probabilities.